Welcome to UGC lecture series Linear Integrated Circuits. So, in this lecture we are going to see about the log amplifier and anti-log amplifier. Log amplifier is an amplifier for which the output voltage is k times the natural logarithm of the input voltage Vin. This is expressed as V out is equal to k into natural logarithm of Vi by V reference, and V reference is the normalization constant in volts and k is the scaling factor. This amplifier gives an output voltage which is proportional to the logarithmic value of the input voltage. To design a logarithmic amplifier circuit, high performance op amps like LM1458 and other series 741, 771 are commonly used. A compensated logarithmic amplifier may include more than one. So, this circuit is a log amplifier circuit for which we have to derive the output voltage as expressed in the previous slide, that V out is equal to k natural logarithm of Vi divided by V reference voltage. So, consider this current as IC. The same current is flowing here as IC, and this is the emitter, this is base. In the circuit, in the feedback path, there is a transistor connected where the base is grounded and the collector terminal is also virtually grounded. We know that these two positive and negative terminals of operational amplifier are virtually equal. So, if the positive terminal is grounded, then this terminal, this negative terminal, this node is also virtually grounded, and if it is given to a positive voltage or a negative voltage, then this voltage is also experiencing the same voltage. Since the difference between these two terminals, the voltage difference between these two terminals needs to be equal to 0 to achieve infinite open loop voltage gain, then we are assuming these two voltages are virtually equal. So, in this case, the transistor is connected in the feedback path, the base of the transistor is grounded as well as the collector of the transistor is virtually grounded, and so this transistor is now acting as a diode. And we can write the equation for the emitter, voltage equation for the emitter as from the diode equation. VE is equal to, first we can write the equation for IE. IE is equal to the saturation current IS into e power QVE by KT minus 1. So, this is the emitter current. Also you can call it as a diode current, since the transistor is working as a diode here. The three out of the three terminals, two terminals are in the same potential, that is the ground potential. The other terminal is connected to the output voltage. So, this transistor is now acting as a diode. So, from the diode equation we have written the emitter current as the saturation current into exponential of QVE by KT minus 1, where K is the Boltzmann constant, T is the absolute temperature, VE is the emitter voltage, and Q is the charge. So, this IE can also be written as IC, since the collector current is approximately equal to the emitter current. So, IC is equal to IS e power QVE by KT minus 1, and this is simplified as IC by IS plus 1 is equal to e power KVE by QVE by KT, and this IS is approximately equal to 10 power minus 13 amps. So, since it is in the denominator part, it is 10 power, if you take it to the numerator part, then this whole term will be very high when you compare it with 1. So, 1 is neglected, and the equation is written as IC by IS is equal to e power QVE by KT. We have to cancel out this exponential term. So, if you take natural logarithm on both the sides, then this exponential term will get cancelled out. So, you will be having natural logarithm of IC by IS is equal to this exponential term will go off, then you will be having the remaining term as QVE by KT. QVE by KT, and from this equation you can write it as KT by Q natural logarithm of IC by IS is equal to VE. So, this is the voltage at the emitter of this BJT. So, emitter voltage is actually reverse of this output voltage. So, output voltage can be written as V out can be written as minus KT by Q natural logarithm of IC by IS. And what is IC from the circuit? If you write V in by R1, the input voltage by R1, if you replace this IC, IC is equal to V in by R1 in this equation, then you will get V out is equal to minus KT by Q natural logarithm of V in by R1 IS. So, this is the output of the logarithmic amplifier. So, here the output voltage is this times constant of the natural logarithmic value of V in. If you compare it with the normal equation, the general equation, it is V out is equal to the constant term natural logarithm of Vi by V reference. You can write these two terms R1 IS, the multiplication of R1 IS as V reference, because these two voltage, the current as well as the resistor are constant. So, you can simply replace the term R1 IS as V reference. R1 is externally connected resistor and IS is the saturation current, which is given as 10 power minus 13 amps. So, these two values are constant. So, I have replaced this as V reference. So, the output voltage is the constant term into the natural logarithm of the input voltage divided by the reference voltage here. So, here there is a drawback in this logarithmic amplifier, which is this saturation current. This will not be a constant value. When the temperature increases, then the saturation current will also get increased, and for that we have to do some compensation techniques. Here the reverse saturation current for diode doubles for every 10 degrees Celsius rise in temperature. Similarly, the emitter saturation current varies significantly from one transistor to another with the temperature. So, it is difficult to set the reference voltage V reference for the circuit. So, this is the drawback. The applications of the logarithmic amplifier are, it is used for multiplication, division and exponentiation. The multiplication is also sometimes called as mixing, and it is used to calculate the dB value. So, always we have when you see the frequency response of any amplifier or integrator, just now in the previous lecture we have seen integrator. In the y axis we have taken the gain, which is in dB. So, dB is calculated as 20 logarithmic value of the normal value. If it is a gain, it is 20 log V naught by Vi, the output voltage divided by the input voltage. So, you have to have a logarithmic value when you calculate the dB value. So, to calculate the dB value of a given quantity, you have to use a logarithmic amplifier. In the direct display of the spectrum analyzer or a digital voltmeter, this logarithmic amplifier is applied, and it is used to find out the true RMS value, and it is used to compress the dynamic range of the signal. When you take a log value of any particular signal, it is actually a dynamic range of the input signal. It is a compressed form of the dynamic range of the input signal, can be seen in the logarithmic amplifier. So just now we have discussed the drawbacks. The saturation current is getting changed with respect to the temperature. So this is a circuit which is used with the compensation techniques. So here this is one logarithmic amplifier with the input voltage Vi, and this is another logarithmic amplifier with the input voltage V reference. Consider this as V reference, a constant reference voltage. In order to obtain the output of the logarithmic amplifier Vi by V reference directly, we have used the reference voltage with the another logarithmic amplifier. So compute these two voltages V1 and V2. These are the input voltages for a differential amplifier. Here A3 is a differential amplifier with all the resistors equal, and this output of the differential amplifier is given to the inverting amplifier here. Since it is given to the inverting terminal, this is an inverting amplifier. Here in the input side of the inverting amplifier, a thermistor is connected. The function of the thermistor is, for a change in the temperature, it is also changed in the resistor value. If there is a change in the temperature in a positive direction, then similar change, the corresponding change will be experienced by this thermistor and the resistor value will get changed. So the output of this entire circuit will be computed or calculated as 1 plus R2 by RTC. This is the gain of the non-inverting amplifier. So you have to connect here a positive terminal, here a negative terminal. The input is given to the positive terminal and the gain is actually 1 plus R2 by RTC. This is the non-inverting amplifier's gain into the voltage output voltage of the differential amplifier. So how this voltage will be obtained? So you have to compute what is V1, what is V2 and V0, and finally the compensated output voltage. So this is calculated as 1 plus R2 by RTC KT by Q, natural logarithm of the input voltage divided by the reference voltage VR. Here this is actually V reference is given directly to a logarithmic amplifier. Here A1, A2 are two logarithmic amplifiers, A3 is a differential amplifier and A4 is a non-inverting amplifier. So now we can straight away write an equation for V1, because we have just now derived the output of a logarithmic amplifier, which is minus KT by Q natural logarithm of V in divided by V reference. V reference is actually R1 IS. R1 is the input resistance, IS is the saturation current. In this case R1 is given and you can call the saturation current of A1 as IS1. So you can straight away write the equation for V1, the output of the logarithmic amplifier A1 as KT by Q natural logarithm of Vi is the input voltage and R1 is the input resistance. IS1 can be the saturation current of the amplifier A1. Similarly, V2 is written as minus KT by Q natural logarithm of the input voltage here is V reference divided by the resistance R1 IS2. IS2 is the saturation current for the amplifier A2, and consider these two saturation currents are equal. IS1, IS2 both are equal to IS, then these two currents are IS replaced by IS1 is replaced by IS. Similarly, IS2 is also replaced by IS. Now what is the output of the differential amplifier? It is V2 minus V1. Substitute V2 minus V1 in this equation. So you will get V out. V2 is KT by minus KT by Q natural logarithm of V reference by R1 IS minus V1. V1 is simply you have to write the output of the logarithmic amplifier A1. So its input is Vi divided by R1 IS. So, consider the input resistance and the saturation currents are equal, and if the voltage is simplified as minus kT by Q, okay, take plus kT by Q out. So, you will get natural logarithm of Vi by R1 Is. So, plus kT, in this case it is if you take kT by Q out, then you will be getting a minus here. It is actually V2 minus V1. So, it is minus of minus V1. So, you will have a plus sign here. So, if plus kT by Q is out, then Vi by R1 Is minus natural logarithm of V reference by R1 Is. So, here these two terms will get cancelled, I1 Rs will get cancelled, and finally kT by Q natural logarithm of, in the logarithmic scale if you have a minus sign, then it can be written as Vi by V reference. This is the output of the differential amplifier. This is the output of this differential amplifier, and finally you call it as V compensation as the output of this A4, a non-inverting amplifier. So, V compensation is just the multiplication of this V0 into its gain. Gain is 1 plus actually RF by R2, RF by R1. RF is the feedback resistance, here it is R2, divided by R1 is the input resistance, it is RTC. So, R2 by RTC. So, 1 plus R2 by RTC into this whole term V0, kT by Q natural logarithm of Vi by V reference. This is the final value, final output of the compensated, temperature compensated log amplifier. So, in this case, if the temperature changes, then there is a corresponding change in the resistor value of this thermistor, and so the voltage will be constant always. If any change in the temperature, the RTC will get changed, and so both the changes will be in a constant range. So, the output voltage will always be constant for whatever the change in the temperature. And the next circuit is the anti-log amplifier. Here before we have seen the derivation of temperature compensated logarithmic amplifier and a basic logarithmic amplifier. And for the anti-log amplifier also, the circuit has two logarithmic amplifiers, and the input signal is given to Vi is given through two potential dividers R2 and RTC again. This is a temperature compensated anti-log amplifier, since we have used a thermistor in the place of one of the potential divider is a thermistor in this case, and Vi is given to the base of the transistor Q2, which is the one of the logarithmic amplifier. A2 is a logarithmic amplifier here, and V reference is again given as the input of the same logarithmic amplifier, and V out, the output voltage is taken at the input of the next amplifier A1. So, you have to see carefully the circuit connection. So, there are two operational amplifiers A1, A2. Both are acting as a logarithmic amplifier in this case. From A1 you are getting the output, and in the feedback path there is a BJT, say it is Q1 for A1, and the emitter of Q1 is connected to the emitter of Q2, which is placed at the feedback path of A2. So, these two emitters are connected. Q1 base is actually grounded and not for Q2. The base of Q2 is not actually grounded. Instead, it is given with the input signal Vi through two potential dividers R2 and RTC, where RTC is a thermistor. And the reference voltage is given through an input resistance R1 to the inverting terminal of A2. The positive terminals of A1 are grounded here. The output is taken at the input of A1 here. So, now there are two transistors used at the feedback path of A1 and A2, and V reference and Vi, the input voltage, is given to the base logarithmic amplifier, and this is the circuit setup. From here we have to derive the output of anti-log amplifier. So, first we have to write an equation for the base emitter voltage of Q1. This is actually V Q1 BE. V Q1 BE is written as KT by Q, natural logarithm of its input. Its input is actually the output voltage. This voltage is given as the input of the amplifier. So, instead of Vi, we will be writing it as VO, V out, by here R1 IS. We assume that the saturation current of both the logarithmic amplifiers or both the transistors are equal. Say IS1 and IS2 is equal to IS. So, simply I have written it as IS. This is the base emitter voltage for the transistor Q1, and the base emitter voltage for transistor Q2 is VBE is KT by Q, natural logarithm of the input voltage here is reference voltage divided by R1 IS. So, this is V reference. V reference is given, and what is VA? What is VA? VA is actually the emitter terminal of Q1. Here we have written VQ1 BE. BE is the base emitter voltage of Q1. So, it is written as KT by Q, natural logarithm of V out by R1 IS. If you want to write VA equation, this is actually reverse of the base emitter of Q1, because the base of Q1 is grounded here, and from the emitter, for the emitter terminal, we have written the equation. Here for VA, it is not so, it is actually reversed for VQ1 BE. So, VA is equal to minus VQ1 BE. So, simply I replace this as reverse of VQ1 BE. So, I include a negative sign for the equation, V out by R1 IS. This is VA. So, from the transistor Q1. Now, what is VB? VB is actually, this is VB. So, through the potential divider rule, we have to write what is VB. So, the voltage across this RTC into the resistance RTC divided by the total resistance. So, this VE is divided across these two resistors. So, VB can be written as RTC into VI divided by R2 plus RTC. So, now we have written VA, VB and the base emitter voltage of Q1, Q2. Write the equation for VA from the amplifier A2. Previously, this VA is written from the amplifier A1. Now, what is the equation for VA from the amplifier A2? So, this is actually VA. So, this point is same as this point, this is VA. So, VA can be written as the emitter, this is emitter terminal. From the emitter terminal, if you take the voltage, then it is the VA voltage. So, emitter base of Q2 plus this voltage, this point, this is also VB, this is also VB. So, this voltage emitter base of Q2 plus VB is the voltage for VA. What is VA? VA from the lower operational amplifier is VQ2 emitter to base plus VB. So, we have written an equation for VQ2BE, just we have to reverse this for EB, emitter to base. So, if you reverse this, then you will be getting minus KT by Q natural logarithm of V reference by R1 IS plus VI into RTC by R2 plus RTC, that is for VB. And what is VA from the upper operational amplifier? That you have to substitute instead of VA. It is minus KT by Q natural logarithm of V out by R1 IS. So, from this equation you have to calculate what is the output voltage, right. So, here keep this equation as such, VI RTC by R2 plus RTC is equal to, bring this term to the left hand side, you have a positive term here for KT by Q natural logarithm of V reference by R1 IS. So, I take minus KT by Q out and you will get, this is positive here. So, I will get V out by V reference. These R1 IS will be getting cancelled. If you bring this term to the left hand side, you will have plus KT by Q natural logarithm of V reference. If I take minus KT by Q out, you will have natural logarithm of V out by R1 IS. If you take this KT by Q out, minus KT by Q out, you will have a plus term for here. So, you will have minus natural logarithm of V reference by R1 IS. So, if you have a minus term in the natural logarithm, then you have to divide. So, V out by V reference. So, take these terms in the left hand side. So, minus KT by Q RTC by R2 plus RTC into VI is equal to natural logarithm of V out by V reference. How will you, okay, if you have to convert this a natural logarithm to the log to the base 10, you have to multiply 0.4343 with the natural logarithm. So, you will be getting log to the base 10. So, both the sides multiply this 0.4343 and take the entire term as k dash Vi after multiplication, and here you will have log to the base 10 V out by V reference. And if you simplify this as V out by V reference is equal to 10 power minus k dash Vi, and V out is equal to V reference 10 power minus k dash Vi. This is the final equation. If you increase 1 volt for the input voltage, then the output voltage will get decreased by 10 times. So, now in this equation if you look at it, then the output voltage will be decreased at the for 10 times if you increase in the input voltage. This is the output of the anti-log amplifier, and these are some questions. Try to answer for these questions. And in this session we have discussed the log amplifier, temperature compensated log amplifier. Also we have discussed the anti-log amplifier, and we have derived the output for the temperature compensated anti-log amplifier also. These are the references. Thank you.